The applied interest of social scientists is piqued by advances in the frontiers of mathematics. The social sciences has benefited from mathematical theory and methods, particularly in the disciplines of economics, demography, psychology, political science, and among others. Computational methods and modern technologies such as geographic information systems are increasingly widely employed to study and simulate social behavior and social systems. Mathematical theories could be used to familiarize issues or questions encountered in society. Many government and societal problems such as voting, power relations, and fair division and apportionment can be more clearly understood and analyzed using mathematics. In this session, we'll look at how mathematics may be incredibly helpful in unraveling the intricacies of social facts and phenomena. The indispensability of mathematical and statistical approaches in the social sciences was acknowledged. In reality, mathematical tools are now extensively used to a greater or lesser degree to aid our understanding of the social world.
Relevant to the upcoming national elections, mathematics has a role to play in our practice of voting. You might think that identifying the winner of an election is just a matter of counting votes correctly. However, there exist numerous mathematical principles behind every election format. For example, the type of elections in the US is different from the election here in the Philippines. To discuss this, we would be guided by the following questions. Is there a best way to conduct an election? That is, what is the fairest way to transform a set of individual preferences into a single societal preference, or the winner? How can we use mathematics to design, analyze, and compare different election methods? And how can we use mathematics to say what fair means? Let us take a look at the mathematics of voting and other underlying principles. The theory of voting is included under what we so-call the social choice theory. This deals with the process by which varied and conflicting choices, as in elections, are consolidated into a single choice of the group or the society, which should reflect the desires of each individual as much as possible. Another principle is that of the order theory. There is an area of mathematics called order theory that studies ways in which objects can be ordered, from simple ordering of integers from smaller to bigger, or ordering of subsets of a set via inclusion, to more complicated relations. Of course, it is fundamental for elections to be systematic, hence the need for an order. Other concepts of voting principles include the ranked voting systems and transitivity. Ranked voting system is basically just a voting system which deals with the ranking of candidates. Here, we can obtain more information regarding the individual choices if we know how the voters rank the candidates. Another concept is that of transitivity. This is an important condition that we want to satisfy for voting systems. Individual preferences are assumed to be transitive in the sense that if a voter prefers candidate X to Y and Y to Z, it is reasonable to assume that the voter prefers X to Z. It is basically just the transitive relation in mathematics. An important question, which is the main theme for discussing voting systems, is that of Kenneth Arrow, which asks, is there an ideal voting system? First and foremost, we should define what the voting system means. Voting system is a way for a group to select one winner from among several candidates. This is basically related to the concept of voting method, which refers to the mathematical process, algorithm, or manner in which individual votes are counted and consolidated to produce a winner. There are 4 common voting methods. First is the plurality method. Second, the board account method. Third is the method of pairwise comparisons. And finally, the plurality with elimination method. Let's talk about the plurality method. The plurality method is the simplest and most commonly used method and is basically just a pataasan ng boto. Here, a candidate with the most number of votes or most first place votes wins. Looking at this example, candidate Tito emerged as the winner with almost 37% of votes. However, This method is questioned because given that the winner obtained only about 37% of the votes, how sure are we that the outcome reflected that of the decision of the voters? Hence, we ask the question, is the winner really the best? There are three scenarios that are possible to question the outcome of the plurality method. Scenario 1 assumes that supporters of Vic and Joey had Tito as their second choice. In this scenario, perhaps Tito indeed is the best candidate. Scenario 2 assumes that supporters of Vic and Joey preferred Tito the least. In this case, we assume that Tito is not the best representative of the voters' preference. And Scenario 3 assumes that one of the 5 other candidates may be perfectly satisfactory to all the voters, including the supporters of the top 3 candidates. That one person may even be the second choice of all. Maybe that candidate should have been the winner. Meanwhile, the board account method, named after French scholar Jean-Charles de Borda, is a weighted voting method. Each place on a ballot is assigned points. If there are n candidates, we give n points for first place, n-1 points for second, and so on until the last place to be given 1 point. For example, if there are 4 candidates, give 4 points to the first place and 4-1 to the second, and so on. Another method is the method of pairwise comparisons. Every candidate is matched on a 1-to-1 basis with every other candidate. The winner of each head-to-head matchup gets 1 point. The winner of the election is the candidate with most number of points. In this example, candidate C is the winner since he got the most number of points. The last method is the plurality with elimination method. This is basically just a sophisticated version of the plurality method and is carried out in rounds. The method starts by eliminating the candidate with the fewest number of first place votes. The process is repeated round by round until a candidate with a majority of first place votes emerges. In the example, candidate B has been eliminated in the first round because he got the least number of first place votes, which is only 4. The table is then reduced to the remaining candidates. For the next round, candidate C will be eliminated because he got the lowest number of first place. In the final round, candidate D emerges the winner because he obtained more first place votes than candidate A.
Other fairness principles. We already know the Condorcet criterion. Now, we'll list other major fairness principles. According to the majority criterion, if a candidate receives the support of the majority of voters, that is 50% plus 1, that candidate shall be declared the winner. Next, the monotonicity criterion states that if a candidate X wins an election and all voters who change their preferences in a re-election do so in any way that is only advantageous to X, then X should still win. As stated in the independence of irrelevant alternatives criterion, if a candidate X is the winner of an election and one or more candidates are removed and votes are recounted, X should still be the winner. Unanimity states that if every individual favors one alternative over another, then the societal choice must reflect that preference. Lastly, non-dictatorship indicates that the outcome should not merely reflect the preferences of a single person while ignoring the preferences of everyone else. Problems with the different voting methods. Earlier, we saw that the plurality method may violate the Condorcet criterion. Does this mean that the other voting methods are better? It turns out that all 4 voting methods exhibit some weakness in the following sense. In a particular election, it is possible that the outcome may violate one or more fairness principles or criteria. So let's study some examples to illustrate this idea. Example 1. The board trustees of a university is choosing its chair. There are 11 board members and 4 candidates. The board will use the board account method to choose its chair. The results of the election are given in the table. Computing the total weighted points for each candidate, we find that B has 32 points since 6 times 3 plus 2 times 4 plus 3 times 2 is equals to 32. C has 30 points, since 6 times 2 plus 2 times 3 plus 3 times 4 is equals to 30. A has 29 points, since 6 times 4 plus 2 times 1 plus 3 times 1 is equals to 29. And D has 19 points, since 6 times 1 plus 2 times 2 plus 3 times 3 is equals to 19. By the border count method, candidate B wins. Now, note that this outcome violates the majority criterion. Candidate A has 6 out of 11 first place votes, a majority, but the Boredom method failed to produce A as a winner. Now, let's take a look at the second example. A student club election is held with 3 candidates, A, B, C. The winner is to be decided by the plurality with elimination method. The preference schedule is given in the table. So, eliminating B, who has the least number of first place votes, we obtain the reduced table. With this round, we see that candidate C wins. However, the election committee declared the election null and void due to some irregularity and asked the voters to cast their votes again. A second election is held, and the 4 voters in the last column of round 1 decided to change their ranking. They switched their first and second choices between A and C, expecting to be on the winner's side after the new election. No other voters changed their choices. Since C won the first election and the new votes only increased C's votes, we expect C to win again. Now, let's determine the winner of the second election. A is eliminated after round 1. B wins in the new election. This outcome violates the monotonicity criterion. Example number 3. The preference schedule for a certain election is shown below. The winner is to be determined using the method of pairwise comparison. Comparing all pairs, A gets 3 points, B, C, and D have 2 points, and E has 1 point. Candidate A wins. The COMELEC, for some reason, wanted to have a recount without new voting. Before they started their recount, losing candidates B, C, and D conceded and requested that their votes be omitted, essentially dropping out from the race. This means that the new preference schedule is now shown in this table. The winner is now E. Originally, the winner was A, but when some candidates dropped out and no revote was made, the winner became E. This violates the independence of irrelevant alternatives fairness criterion. We have presented an election where 4 different methods produced 4 different winners. So, we have presented instances of elections using certain voting methods where particular fairness criteria were violated. It seems we are nowhere near an answer to the question, is there a best method? It is good to know that experts would not have an immediate answer too. Most would declare there is no ideal voting method. The mathematical basis for this is a very famous and deep theorem of a mathematical economist, Kenneth Arrow. We will talk about that in the next slide. Arrow's impassibility theorem. Kenneth J. Arrow, in full, Kenneth Joseph Arrow. Born August 23, 1921, in New York, United States. And died February 21, 2017, in Palo Alto, California. Mathematical economist known for his startling thesis built on elementary mathematics, the impassibility theorem or Arrow's theorem. In his PhD dissertation, Social Choice and Individual Values, He looked into these topics. In 1952, he wrote A Difficulty in the Concept of Social Welfare, an essay that summarized his findings. In 1972, Arrow was awarded the Nobel Prize in Economics. This theorem states that there is no consistent method by which a democratic society can make a choice that is always fair, when that choice must be from among three or more alternatives. The concept of fair is taken in the sense that a fairness principle or condition is not violated. Arrow's theorem applies to ranked or preferential voting systems. The mathematical proof uses concepts of order theory. It proves that no voting method can satisfy all reasonable fairness criteria at the same time. There are other voting methods that are also used, even in some legislatures. An example is approval voting. In this system, voters are not asked to rank the candidates in order of preference. Given a set of candidates, voters can give their approval to as many or as few of their choices. Voting experts consider this a strong system, but more applicable to small voting populations, like some legislatures or organizations. This method works for those voters who cannot or who prefer not to make distinct rankings among the candidates. According to the advocates of the method, approval voting is easy to understand and simple to implement. It gives voters flexible options and increases voter turnout. It helps elect the strongest candidates, unaffected by the number of candidates, and it will reduce negative campaigning. Also, in the approval method, minority candidates are not greatly disadvantaged. We discussed 4 voting methods, which are really methods of counting or consolidating individual votes. The 4 voting methods are plurality method, border count method, method of pairwise comparison, and plurality with elimination method. The fairness principles are Condorcet criterion, majority principle, monotonicity, independence of irrelevant alternatives, unanimity, and non-dictatorship. Arrow's impossibility theorem demonstrates that no voting method will always satisfy all fairness criteria in all voting instances.
Now, let us proceed to weighted voting systems and the measurement of power. In many elections, even in our upcoming election in May 9, the principle of one person, one vote is followed. This is the principle we follow when we elect national and local officials. However, in some voting situations, individuals or groups are not always equal and some voters are given more say than others. Weighted voting systems are systems where voting rights are not equally divided among all its voters. Some examples are corporate shareholders meetings, where each shareholder has as many votes as the number of shares owned, and committee voting where the chair has tie-breaking or veto power. However, you may ask, who has more say in weighted voting systems or who has more power? How is power measured? Is there a mathematical treatment of power? To discuss weighted voting systems, for simplicity, we will analyze voting situations involving only 2 alternatives, such as a motion involving a yes or no vote. We also assume that no abstentions are to be made. A weighted voting system has 3 main ingredients, namely the players, weights, and quota. For the players, who are the voters, if there are n players, denote them by P1, P2, up to Pn. And if each player controls a certain number of votes, called the player's weight, denote this by W1, W2, up to Wn. The quota or Q is the minimum number of votes needed to pass a motion. The quota is usually a strict majority, usually 50% plus 1. But rules may require a higher number of votes, even 100% or a unanimous one. but the quota must satisfy half W1 plus W2 up to Wn is less than or equal to Q, which is less than or equal to W1 plus W2 up to Wn. So we present the above information using the following convenient notation: Q, W1, W2 up to Wn. The notation indicates a weighted system with quota Q and N players. The weights of the N players are listed after the quota. The weights are ordered from biggest to smallest. For our first example, we could see that there are 6 players, P1, P2, P3 up to P6, with weights 8, 6, 4, 3, 2, 1 respectively. The quota or number of votes to win is 13, so there are 24 total votes. For our second example, since the total number of votes is only 20, no motion could ever pass because the quota is too high. This is not a valid weighted system. Next, the quota is less than half the total number of votes. If P1 and P2 voted yes, and P3 and P4 voted no, both groups win. So this is not a legal voting system. For our fourth example, 20-7-7-7-7, 3 players need to vote yes to meet the quota. In this case, all players have equal power and this is essentially just a one-person, one-vote system. It can equivalently be described by the system 3:1-1-1-1. For our fifth example, the first player can pass any motion alone. Such a player is called a dictator. A player whose weight is bigger than or equal to the quota. In systems with dictators, all the other players have no power. A player whose vote has no outcome in the election is called a dummy. In this system, the last 3 players with the weights 3-1-1 are all dummies. For our sixth example with the quota 8 and the weights of the players 7-3-1-1, player 1 is not a dictator, but he can single-handedly prevent any group of players from passing a motion. Player 1 is said to have veto power. 7. Does player P3 really have very little power compared to P1 and P2? Observe that P1 cannot pass a motion without the help of P2 or P3. Similarly, P2 and P3 need votes of at least one other player. At least 2 players are needed to pass a motion. In this case, we see that P3 has just as much power as the other 2 players. This example shows that in a weighted voting system, a player with the most number of votes does not necessarily hold the most power. For our 8th example with the quota 51 and the players' weight as 26, 26, 26, and 22, 4 partners hold these shares respectively. The weights are almost uniform. Can we say that all 4 players more or less have the same power? Not necessarily. The last shareholder is really a dummy. P4 has no power. The weight of P4's vote, which is 22%, even if close to the others, is not enough to make a losing coalition win or a winning coalition lose. In this example, the first 3 partners share equal power, but the last has none. And for our last example, with quota as 15 and the players' weight as 5, 4, 3, 2, and 1, all votes are needed to meet the quota. Then, this needs a unanimous vote. Thus, each vote counts as much as the other. The system is equivalent to 5:1-1-1-1-1 and is essentially a one-person, one-vote system. We should thus regard the one-person, one-vote principle to mean that all players have an equal say in the outcome of the election, instead of just having an equal number of votes. Now, let us proceed to Banzhaf index and the mathematical measurement of power. As shown by the examples, a player's power cannot be measured simply by the number of votes he or she has. For instance, if player X has 4 votes and Y has 2 votes, we cannot conclude that X has twice as much power as Y. Of course, if 2 players have the same number of votes, we expect them to have the same amount of power. There are several measurements of power, but we will focus on the method suggested by lawyer John Banzhaf in 1965. His idea is that power is measured by winning. The player whose vote can influence the outcome of the election the most is the one with the most power. So revisiting example 7 from the last slide, with its quota as 51 and the player's weights as 48, 47, and 5, there are 4 groups that could join forces to form a winning combination. P1 and P2 with 95 votes, P1 and P3 with 53 votes, P2 and P3 with 52 votes, and all 3 players with all 100 votes. A coalition is any set of players that join forces to vote together. The total number of votes in a coalition is called the weight of the coalition. Winning coalitions are those with enough votes to win, otherwise they are called losing coalitions. Let us list the different coalitions in the weighted voting system given in example 7. We could see that there are 3 losing coalitions and 4 winning ones, but coalition G is called the Grand Coalition. Let us look at the winning coalitions for this system. In each of the coalitions D, E, and F, both players in the coalition are needed for the win. In G, no single player is essential. A player whose desertion turns a winning coalition into a losing one is called a critical player or a pivotal player. That is, a critical player is a voter who can cause the measure to fail by changing his or her vote from yes to no. For the Banzhaf Power Index, the critical player concept is the basis. Banzhaf's key idea is that the player's power is proportional to the number of times the player is critical. In the previous example, each of the 3 players is critical twice, so all have equal power. We say each player holds 1/3 power or that each has Banzhaf Power Index 1/3. The triple 1/3 is Banzhaf power distribution for the 3 players. To calculate the power of a voter using the Banzhaf Index, we should first make a list of all coalitions with n players. One has 2n-1 coalitions. Next, determine which are the winning coalitions. Third, in each winning coalition, determine who among the players are critical players. Next, count the numbers of times player P is critical and call this number CP for critical player. Count the total number of times all players are critical and call this number T. The Banzhaf Power Index of player P is given by the ratio Cp over T. That is, power index of player P is equal to the number of critical instances of player P over the number of critical instances of all players. Practicing this for example 10, we compute the Banzhaf distribution for the system with a quota of 4 and the players' weights as 3, 2, and 1. For step 1, there are 7 possible coalitions. Then, proceeding to step 2 and 3, we determine the winning coalitions and critical players. And the winning coalitions are AB, AC, and ABC. And we could notice with step 4 that A is critical 3 times, B is critical 1 time, and C is critical 1 time as well. So for step 5, T is equal to 5 total critical instances adding A plus B plus C and their critical times. So the Banzhaf power distribution is 3/5, 1/5, 1/5 with power indices. So that is their corresponding critical power. But for any voting system, the Banzhaf power index of each player is 1 over n. 2 proportional systems always have the same Banzhaf power distribution since they would end up being equivalent. And in any 3-player voting system with no veto power, there is only one possible power distribution, namely 1/3, 1/3, 1/3. But what is the mathematical reason why a committee could not seem to obtain a strictly decreasing power distribution that reflected the decreasing weights? This is given by the following theorem obtained by John Tolle and discussed in his paper, Power Distribution in 4-Player Weighted Voting Systems, published in Mathematics Magazine in 2003. In this theorem, he discusses that in any 4-player weighted voting system with no veto power, there are only 5 possible power distributions as listed below. In particular, there is no strictly decreasing power distribution for a 4-player weighted voting system. And that is the discussion for this part of the lesson.
Power distributions in some institutions. The United Nations Security Council is composed of 5 permanent members, namely the United States, the United Kingdom, China, France, Russia, which all have veto power, and 10 non-permanent members which are voted into the committee with fixed terms. More so, a winning coalition must consist of the 5 permanent members plus at least 4 non-permanent members. To visualize it, the voting rights in this council has a weighted voting system of 5 sevens and 10 1, with a permanent member having 16.7% and a non-permanent member with 1.65%, giving more power to the permanent members than the latter. Moving forward, in the United States, their president is chosen using the system of the U.S. Electoral College. It was first proposed in the year 1876 and continues to be the preferred system for choosing the country's highest position. So, this is how the system works. The 50 states are given the power to cast certain amount of votes equal to the total numbers of members of Congress, including the senators plus representatives from that state. These are then casted by electors chosen to represent their respective states. More so, DC, or the District of Columbia, is considered as an additional state having 3 electors. Although the system might seem complicated as compared to our electoral system in the Philippines, individual citizens will still cast their votes, and then this will become the basis for the Electoral College winner-take-all system. The only difference is that the U.S. Electoral College can be seen as a weighted voting system. To give an example, in the presidential elections of the year 2000 in the United States, the Electoral College results proclaimed George W. Bush as winner over Albert Gore, having 271 electoral votes, while the latter gained 266 votes. However, if the votes were counted individually and not by state, Albert Gore would have won as he garnered 50,996,064 votes, whilst Bush had 50,456,167. Following the electoral system of our country, the slight difference of 500,000 individual votes could have made Albert Gore won, which unfortunately is not the case in the United States. Likewise, the sizes of the states and their population matters in this system, as well as bigger states like California are given higher electoral votes than those of states with smaller population like Alaska. To visualize it, here is the table of the states and their corresponding electoral votes. With that being said, the imbalance in electoral votes affects the campaign strategies of candidates. And finally, to be elected as a president, a candidate only needs a total of 270 electoral votes out of 537. These are not just 2 examples of how power is distributed in voting systems. Rather, it is a peek on the systematic mathematics of power. Fair division and apportionment. In the context of social sciences, the concept of fair division can be applied in the division of certain set of goods among individuals that would be considered fair by the parties involved. As an example, let's say an old farmer, which is a father to 3, is near his death. He has 17 goats as his assets, and he set his will as follows. 1/9 of the herd will belong to the youngest, 1/3 will belong to the middle child, and the half will go to the eldest. So to satisfy their father's will, the siblings divided the goat by adding an imaginary 1 to the total number of goats, making it 17 to 18 for easier multiplication of fractions. Therefore, the 1/9 of 18 is 2, which he gives to the youngest. 1/3 of 18 is 6, which the share will belong to the middle child, and 1/2 of 18 is 9, the eldest's inheritance. Adding it all up, 9 plus 6 plus 2 is 17. Although the number of units may be seen as unfair as some gets way more than the other, it isn't. This can be still called as a fair distribution as every party considered it fair while fulfilling their father's wishes. Moving forward, here are the properties of a system that follows fair division. First, it must be decisive. If rules are followed, a fair division of the set is guaranteed. Second, it must be internal to the players. It does not need to require intervention of an outside authority such as a judge, arbitrator, or the like. For the third and fourth, there are two assumptions that need to be followed. First one is that it must assume that the players have no knowledge about each other's value systems, and the last one is that the players are rational or that they use logic instead of emotions. Likewise, to address other problems in fair division, the method of apportionment may be used. Apportionment is the process of allocating identical, indivisible objects among participants entitled to unequal shares. As an example, the problem of assigning congressional seats is aided by the method of apportionment.
Now that we're done with fair divisions and its components, let's go over to some of the quota methods and the paradoxes from the quota method. Let's first define quota methods. They are apportionment methods that satisfy the quota rule. In this segment, we will present two quota methods proposed by Alexander Hamilton and William Montes. We will now apply the fair division problems and computations that we discussed a while ago. Starting with the Hamilton method, we'll try to explain this given example step by step. A mythical country with 3 states, A, B, and C, has a total population of 1 million. There are 100 seats to be apportioned to the 3 states. The standard divisors, therefore SD is equal to 1 million, which is the total population divided by 100, the number of seats, equal to 10,000. By using the Hamilton method, the first step will be by calculating each state discussed a while ago. To solve for the standard quota, you'll need to divide the state population by the standard divisor. So for state A, 657,000 divided by 10,000, that will be 65.7. State B, 237,000 divided by 10,000, 23.7, and so on. Next step on the Hamilton method is to assign each state its lower quota. Now usually, we round off by changing the number to the closest whole number, taking into consideration the digit to its right, when if it is greater than or equal to 5, you add one value to the digit. If it's less than, then it will stay as it is. As presented in the table, the usual round-off of 65.7 would be 66, but since we'll use a lower quota, we'll take the number as it is. So for state A, 65.7 will be just 65, state B with 23.7 will be 23, and state C with 10.6 will be 10. By using this lower quota, you'll notice its total is 98, two values less. So for the last step, give surplus seats one at a time to states with the largest absolute fractional parts until you run out of surplus seats. So in this example, state A and state B with 0.7 absolute fractional parts will get one additional seat each. The total allocation for states A, B, and C will be 66, 24, and 10 respectively. This will complete the total apportioned seats for the 3 states. Now using the same example, let's use the longest method. We'll start out as in Hamilton's method by getting the standard quota, usual round-off, and lower quota. However, for the next step, assign surplus seats using relative and not absolute fractional parts. This means we divide the fractional parts of the quota by the integer part of the quota. Now let's first figure out how to solve the relative fractional part. For example, the standard quota is 41.82. This will be divided into 2 parts, the fractional part, which is 0.82, and the integer part, which is 41. Now, as stated a while ago, we need to divide the fractional part by the integer part. That will be 0.82 divided by 41. This will result in 0.02, which is now the we continue to do this in our example, we'll be able to get the answer for state A, which is 0.01, state B with 0.03, and state C with 0.06. Then now we'll give the surplus seats one at a time to the states with the largest relative fractional parts until we run out of surplus seats. The total allocation for states A, B, and C will be 65, 24, and 11 respectively, which will complete the total apportioned seats for the Hamilton and Lowndes are quota methods. Both used the standard divisor and standard quota. Both satisfy the quota rule, which is standard quota is rounded up or down to the nearest whole number. Before we discuss the paradoxes from the quota method, let us first define a paradox. It is a seemingly contradictory statement that may nonetheless be true. It is an assertion that is essentially contradictory, although based on a valid deduction from acceptable premises. Paradoxes are often statements or situations contrary to received opinion or are counterintuitive, and quota methods are open to problems and paradoxes. We will illustrate 3 paradoxes arising from application of quota methods in the succeeding 3 examples. First one is the population paradox, wherein an increase in the state's population. Let's see this example. Recall the allocation using Hamilton's method in our mythical country with 3 states, A, B, and C. Suppose that the population grew to 1,010,000. We recompute standard quotas and apply Hamilton's method again. The result would be that A's population grew but lost a seat, however C's population decreased but gained 1 seat. Next is the Alabama paradox. An increase in the total number of seats to be apportioned causes a state to lose a seat. In this example, after the population grew in our mythical country, Congress decided to allocate 101 seats. Let's see what happens when we reapportion using the Hamilton's method. When the House only had 100 seats, C was entitled to 11 seats. But when the House increased to 101 seats with no change in population, C only got 10. Lastly, the new state paradox. Adding in a new state with its fair share of seats can affect the number of seats due to other states. Now in this example, suppose that we have a new fake city and it has 2 schools, Dilao and Pula. Mayor Mocha donated 100 computers that were apportioned using Hamilton. But a new school, Bato, is created with an initial enrollment of 525. Mayor Mocha then decides to add 5 computers to the pool of computers. After this is done, a recalculation of the allocation is made. This is the result. The addition of a new school can, by itself, affect the apportionment of others. Now that we're done with the quota methods and its paradoxes, we also have here our divisor method. There are apportionment schemes where the standard divisor and standard quota are not used. Instead, a modified divisor is used to obtain modified quotas that will result in no surplus seats. The modified quota is obtained by dividing the state population by the chosen modified divisor, that is, MQ is equal to state population divided by MT. These apportionment methods are called divisor methods. Later, we'll present 3 divisor methods. The 3 methods differ in the way modified quotas are rounded off. These proponents were the American statesmen Thomas Jefferson, John Quincy Adams. For the Jefferson method, similar to what we did in the other methods, calculate each state's standard quota and assign each state to its lower quota, giving 6, 2, 1 for states A, B, C respectively. If there are surplus seats, modify the divisor so that when each state's modified quota is rounded downward, no surplus seats remain. Since this gives 9 seats, modify the divisor by choosing a smaller divisor, let's say 98, to get a bigger allocation. Assign lower quotas using the modified quota and apportion to each state the integer part of its modified quota, which in this case is 7, 2, and 1 for states. Here is a table for this example. Next is the Adams method, where we also start by calculating the state standard quota. However, we'll assign upper quotas based on the standard quotas, which will give 7, 3, and 2 for states A, B, and C respectively. In this case, since this gives 12 seats, which is too much, modify the divisor by choosing a larger divisor than 110, let's say 135, to get smaller allocations. Assign upper quotas using the modified quota and apportion to each state the upper integer of its modified quota, which in this case is 6, 2, 2 for states A, B, and C. Here is the table for this example. Lastly, the Webster method, where we also start by calculating the state standard quota. However, we'll round off the standard quotas in the usual way, which will give 6, 2, and 1 for ABC, respectively. In this case, since this gives only 9 seats, modify the divisor by choosing, let's say, 107.2 to get larger allocations. Round off the modified quotas in the usual way and apportion to each state the integer of its modified quota, rounded off in the usual way, which in this case is 6, 3, and 1 for states A, B, and C. Here is the table for this example. Here is a table to show the comparison of the apportionment using the three methods. We see that after using the three divisor methods, we obtain three different apportionments. It is known that the three divisor methods can violate the quota rule, unlike the Hamilton and Dundas method, which do not violate the quota rule. However, it can be proven that none of the three divisor methods can suffer from the earlier paradoxes, also unlike the Hamilton and Dundas. After discussing all these methods, questions often arise, such as which method is better, or a quota method or divisor method. Among the different methods is the best one. Advocates of particular methods continue to disagree, but the following result of mathematicians Michael Belinsky and H. Peyton Young, called the Belinsky and Young impossibility theorem, is known. It asserts that no apportionment method is mathematically flawless in the following sense. According to them, any apportionment method that does not violate the quota rule must produce paradoxes, and any apportionment method that does not produce paradoxes must violate the quota. And to summarize their major properties, here is a comparison table of the 5 methods. For additional information, the apportionment method used by the U.S. Congress to apportion congressional seats is called the Huntington-Hill method. This method was proposed by statistician Joseph Hill and mathematician Edward Huntington in 1911. It was adopted officially by the U.S. Congress in 1941 with a fixed house size of 435. The method is similar to the Webster method, except that rounding off is based on the geometric mean instead of the usual arithmetic mean. The geometric mean of x and y is the square root of the product of x.
In this module, we presented the use of mathematical theory to familiar issues or questions encountered in society. Many problems such as voting, power relations, and fair division and apportionment can be more clearly understood and analyzed using mathematics. For the recap, in Section 1, Arrow's impossibility theorem shows that there can be no perfect system. In Section 2, we are reminded that in any society, no matter how democratic, some individuals and groups have more power than others. And finally, in Section 3, the problem of how to divide certain sets fairly was examined and applied to the process of seat allocations in Congress. The concept of order is ubiquitous and important in mathematics, especially in decision making. It allows us to analyze voting systems and other social issues, but it does not provide all answers.